And I don't remember if I was bringing it to your attention, or maybe you knew it before. The GRFP, graduate fellowship, graduate research fellowship by National Science Foundation. Did you hear about it before?
I have not.
Okay, so there is a call for proposals that are submitted not by faculty but by graduate students or undergraduates who are planning to become graduate students, and the call is the deadline is something like by the late October, and the winners are announced about now by the mid of April. So if one wins this fellowship, it is like 4 years of full stipend plus some travel and book allowance. So basically, and with this stipend, one can change the graduate school, like immediately go to MIT and tell like, hey, I have my own stipend, would you let me to study there? And why I started speaking about it, because in reviewing these proposals, reviewers need to assess two criteria: intellectual merit, which is more specialized professional thing, and broader impact, which is how much this finding and research activities are contributed to education of general public and stuff like that. So if you may consider this option, and it's like three pages research statement, or even 2 pages, which is very doable. Hi Yang Chao, hi Rebecca. I am happy to see you connected.
I'll shut my camera off so you don't have to be distracted by my cat.
No. We are happy to see your cat. My cat is relaxing right now. He doesn't want to assist in today's lecture. Hello, Mahek. Nice seeing you connected.
Hello.
She's trying to eat my toast.
Does your cat bite you, or I mean, not aggressively, but as attracting attention?
All the time.
Oh, okay. So I'm going to put sharing screen. Hi, Jofan. Nice seeing you connected. Okay, so I'm going to mumble something about our research projects, about like third part of time, then another third of time I will go over what we did before in the lecture material, and then there will be some new materials. So we are in the class of computational chemistry that poses a goal of modeling materials and molecules and predicting their properties. We are very close to accomplishing theory background, and you basically know all the facilities and software that can be used, at least in the frame of this course. And we are approaching to accomplishing research projects, and there are some there were elected subjects of research. So Raju is decided to explore solid electrolytes. Amir wanted to look for conjugated polymers, which are really good and interesting subject, because it with experience and interest of Amir that he got before and what we get in class, it could be a merger of mechanical properties and electronic properties. So it could be like competitive research. So when you are done with dimer, please let me know so that I can look on it on the cluster. By the way, NERSC Quarry is back fully operational since 3 a.m. In the night, and I've checked this morning. It works well, so it is open for use. So please consider to transfer your models to NERSC and proceed as we planned. So Zhao Fan decided to go different, not what is shown here. Cellulose, right?
Right. Nanocellulose.
Nanocellulose, okay. Cellulose. Okay, and I'll remove this diagrams. Yang Chao decided to pursue the carbon nanotubes with a real ring functionalization, and yep. So please consider to move the files and optimize them as a first step on NERSC and proceed further. Everyone is encouraged and invited to send me emails as soon as you see some roadblock in your projects. You do not need to wait until Wednesday. I put these projects for the class as my top priorities above all other activities, so I will try to reply as soon as possible and contribute to log in and see if there are any problems with the files. So Mahek is pursuing phospholipid bilayers, and I think after initial optimization we can chat more about whether to pursue this toxic materials that are used for disinfection, or maybe there will be some additional ideas. I do not see Salim for a couple of meetings. Probably need to send him an email, but his chances are not yet lost. And based on his choice, it is a very competitive project. But Salim, if you're listening to this, you need to log into meetings and participate. So let me talk about Stephen selected the metal organic complexes for catalysis. I didn't update the figures here, but it is ruthenium in different oxidation states, 2, 3, and 4. And the idea is that the complex, so ruthenium is traditionally, just by metal organic transition metals, prefer to stay coordinated with ligands, and ruthenium ion traditionally prefers octahedral coordination with 6 ligands. So the model that Stephen is pursuing, the ligands are arranged in such way so that out of these 6 spots, PO3, 5 are occupied. 5 are occupied by stable ligands, and the 6th place is, so to say, available for chemical reactions. So in one of the oxidation states, it coordinates with water from the solvent, and in other oxidation states, it can kick hydrogens off and modify water into like oxygen. So it is related to oxidation reaction. And the selected project by Rebecca was in graphene flakes, and the graphene flakes do have interesting property. So graphene itself, infinite honeycomb sheet, has band gap same as for the metal, zero gap. But if one carves smaller pieces of this graphene, the gap increases. And there are some calculations in this figure here from literature that as one approaches smaller and smaller size of the flake, the gap increases. So it goes up, like benzene is the ultimate case when the gap in the UV range, and for the larger things it will be in the visible range. So there are several open challenges in this project, and as main author Rebecca will decide what she wants to pursue, but one way is how to make this graphene or graphene oxide quantum dots to keep their oscillator strengths between HOMO and LUMO to be optically active, but move the emission into the infrared region. So infrared emission of these graphene quantum dots is a challenge that is not yet accessed. On the other hand, there is in order for them to be practically usable for industrial applications and for bioimaging, for medical applications, they need to be soluble. One needs to be able to dissolve them in water. So plain hydrogen compensated graphene flakes cannot be solved in water. One can sonicate it with ultrasound, but they will sediment very quickly, and to make them colloidal, one needs to place different sort of surface functional groups, and set of these functional groups is one can dig something out of literature, but it is not 100% positive knowledge. So Rebecca may try different functional groups and see whether they will keep this graphene quantum dot optically active on one hand, and whether it will be stable structure on the other one. And to make it infrared active, one can dope it by covalent doping in the middle. Okay. So research procedure is very specific for each project. There are no, one cannot generally use the same protocol, but we may try to have some unified motifs. So if you're already sure about your model, if you have optimized and you know what your model is, you may create at least 2 data sets. one dataset a model with when geometry is optimized, another when it has experienced molecular dynamics with elevated temperature, so end of the trajectory. And then for these two data sets, you perform computational characterization, for example, making density of states and spectrum, and then compare them. So it is like a minimal set that can be a good starting point. For example, this is a very appropriate for Raju because he's looking for ionic conductance when ions are moving through the solid electrolyte due to the heat. This would be appropriate for the project with cellulose because hydrogen bonds may break if you heat it. This can be appropriate for conjugated polymer because upon molecular dynamics trajectory, the structure will bend, and these bending angles across the model will affect electronic properties. And for metal-organic complexes, upon heating, the ligand may desorb completely from this metal center. And I want to bring to your attention another quite general thing. We are not yet here, but as you progress through research projects, the most important common thing is to create a map. It's not for me, it's only for the main author, for the author of the project, to create a map of directors. So in maybe I can put ground here. So for a given model, one can look on the ground state, one can look dataset thermalized state, or after molecular dynamics. One may have a directory specifically for density of state, specific directory for spectrum. Lifetime and multiple key points, I will mention if any of the projects will need it. It could be about lifetime. I plan to speak during today's lecture, and multiple key points will be most by good luck applicable to the project of Amir. I didn't knew that you're going to do conjugated polymers, but for them the dispersion along key points may bring some scientific insights. Also, I'm going to focus on the rest of the table in here, and this part can be applicable to everyone, but primarily this is of the critical interest and importance for Steven, for catalytic metal-organic complexes. So all these protocols, like spectral density of states, originally can be done for the ground neutral spinless, like multiplicity for singlet neutral ground. But based on chemical intuition and just for systematic exploration, one may find that the specific model is more stable in presence of additional counter ions, or if we do not include counter ions explicitly, it could be stable if we change the total charge. Like if it is, if all your ligands are neutral, and you know that a metal organic complex is most stable for ruthenium like 3+, then one needs to remove 3 electrons from the system. So I would say it will be anion 3+, and then one would need to run calculation for the model in this spot, and maybe then repeat all spots for spectra and so forth. If the model does have unpaired electrons, it immediately means that it should be spin polarized calculation. Initial geometry optimization is good to perform without it, but productive cycle is better with spin polarization. So one may change charge and later enable spin and later change multiplicity, and also one may explore system in the excited geometry if the electron is promoted to HOMO to LUMO. So which will means that chemical reactions can be activated by photoexcitation. So there are several options, and we'll discuss it in person for each individual project. But as planning your research, it is important to create a homogeneous tree of subdirectories that you can navigate through. So if there will be like a dozen numerical experiments, dozen directories, it's worth of naming them in the appropriate way. And I have forgotten to mention that orbitals could be very intuitively helpful for analyzing properties of molecules. Okay, any questions about the projects? Okay, I do not hear any objections or questions. If you follow the calendar, when is our last day of class? Or last week of class? Do we have 2 weeks more or 1 week more? I do not know right now, but we may discuss it on Tuesday. So please check academic calendar. I will check as well, and we'll make a specific plan. So why I'm bringing it to your attention, let me play open cards and share the plans, how we manage time and what is expected. So first, I assume that everyone welcomes and votes for projects being main outcome of the course. So no one wants exam based on theory background. So if anyone wants a theory background exam, let me know, and then we'll make a vote what is the majority. But I assume even without formal votes that projects are more welcomed. Second, right now let's focus on generating data. But in addition to getting some positive results, there will be 2 forms of the reports. The written reports of the projects, which will be due on the last day of class, and the presentations, which will be on the day which is scheduled for as an exam. If I will consult with everyone about the dates, we can do otherwise, like second last day reports and truly last day of class the presentations. And I need to count days in the academic calendars and announce when the results should be done and converted in these forms. Just giving you a little heads up. So let's go to the review what we did in last few lectures. So right now our goal is to create a theory or get a theory that is designed to describe excited states, and we are practicing this definition, update of the definition of density. So instead of coinciding orbitals, we are using non-coinciding pair of non-coinciding orbitals. Summation goes over all possible pairs of orbitals, but relative weight, how given pair of orbital contributes to the density of electrons, is determined by this density matrix. This density matrix is chopped onto 4 segments: ground segment from 1 to HOMO, both indices; excited segment, both indices from LUMO to infinity; and then transitional densities, when one index runs from 1 to HOMO and another one from LUMO to infinity. The relative when system is being this transition densities and excited densities appear only if system is excited by light, and if light is not very intense, then if it is considered as a perturbation, the contributions to transition densities are bigger than to excited densities. In this example, we give explicit indices for elements of density matrix in each segment, and the goal of the basic theory for excited state calculations is to find what is highlighted here by blue and yellow, the transition densities. These matrices, transition density matrices, are typically stored in a form of vectors to allow for to formulate the problem as matrix diagonalization. And often in the community one calls these transition densities as X and Y. So in some sense, the goal for this chapter is find X and Y as function of incident light frequency. Okay. And at the end of last lecture, we did cover the concept of Franck-Condon principle and the Stokes shift. So this is deviation from our main train of thoughts, from our description of excited states, because when we were speaking about ground state only, we were assuming that geometry is given once and forever. It is in the geometry is either in the minimum, optimized minimum of geometry, or it is shifted somewhere. But when deriving Hartree-Fock theory and the density functional theory for ground state, we were not thinking about additional effects due to motion of nuclei. But if you are speaking about excited state, one needs to take into account that potential energy surface for excited state often can be different from the potential energy surface for the ground state. And if we are designing a theory for excited state, we need to remember this fact. If you want to neglect it, it needs to be pronounced as an approximation. If you want to take it into account, then the theory will become more complicated. The quantitative measure of how this effect of this effect can be expressed in several ways. One is just how far equilibrium position in ground state and excited states are offset from each other along the nuclear coordinate. Another measure is how much yellow line in here is longer than black line here. How much the transition energy of absorption differs from transition energy of emission. And this feature, this difference is referred to as Stokes shift, and it is very often observed in experiments, even for rigid models. And for soft models, this effect is noticeable. For any organic molecule, it is noticeable effect, and it belongs rather to organic physical chemistry, spectroscopy, rather than computational chemistry, but we should be aware of this. So this is where we finished our previous discussion, and now let me go to the new material. So the plan for today, I'm still postponing or trying to postpone the actual theory for x and y as a function of omega. This time we will get the equations that by solving which one is getting this transition density matrices and eigenfrequencies at which system accepts energy. But I have a big fear to scare everyone away from this important subject by going deep into equations. So before we get actual theory that generates this transition densities, I suggest we discuss what would we do if these transition densities are available. How, if we get them calculated, how they are connected to a real world. And why one needs optical excited states, why one needs optical properties, and how to think about them, how to process data related to optical properties. Before we go there, I want to give a very little note that I'm always forgetting through the years, but any research projects that deal with charge transfer may need this little comment. And please remind me, I'll try to recall myself on the next lab. There is a way to convert three-dimensional part charge files into one-dimensional distribution by integrating over x and y dimension. And also there is a way to find dipole of static dipole for each orbital. So if this could be useful for radio, for ionic conductors. So if three-dimensional orbital looks like a map, then this one-dimensional integrated rho sub I of z will look only as a one-dimensional function. And if one needs to analyze like hundreds of orbitals, looking at one-dimensional function is much easier. And if charge density in one orbital and another orbital migrates in space, it is easier to assess on such one-dimensional things. Okay. So, what do we do if you know transition densities, or what are the main observables in computational spectroscopy? If you want to describe interaction of light with matter, if you want to describe color of the material. Stephen, can you comment on this? Like, what is important if we need to assess optical property of a molecule? just briefly give us direction of thought.
I believe the critically important part would be the dij squared, since that would be the total change between the base and the excited state.
Okay.
Just a thought.
Okay. And what is dij?
It's the difference between the initial state of the position of the initial state of the electron in question and the final excited state. Right?
Okay. I never thought about it in this way, but it's not wrong. Huh, interesting. Yeah, thank you, Stephen. I would call it expectation value of position operator, just more mathematical. And Rebecca, thank you for identifying the dates in the schedule. I'll take it in mind. So expectation value or matrix element of the position operator. So this transition dipole is a vector, and as Stephen correctly told, it is transition between initial and final. And since it is a position is a three-dimensional vector, this transition dipole has three components: x, y, and z. So with this x, y, and z in between the orbitals. Here it should be integrated over all three: dx, dy, dz. And as soon as one computes these three components for given pair of orbitals, one can find the absolute value squared. And I know this is a basic thing you all took linear algebra, just bring to your attention. So if you write down this x, y, and z component as a row vector and as a column vector, then row by column will give this square of the x component, square of the y component, square of the z component, which will be the transition dipole square. So the length of this squared length of the transition dipole determines, is a quantitative measurement of ability of electron being promoted from orbital I to orbital J under optical excitation. And thank you, Stephen, for helping to think about these aspects in the right way. So we were speaking before about the oscillator strength, and we were telling that it is transition dipole squared multiplied by constant. I think now it is time to speak with more details. What are these constants? And it's not I'm not sure that the word constant is ideal, because it includes frequency of light, which will be different depending on the energy of set of these orbitals. So the constants, and there are ways to derive them, but we need to rush through the course, and derivation would take too much time. So there is a energy of set. So if the transition happens at higher energy, it will be, there will be additional factor that will make it more intense. There is Planck constant, there is a mass of electron and charge of electron, and there is a factor of 4/3 pi, which comes from the fact that if you have linear polarized light and random ensemble of the molecule can be oriented at each angle, at any angle in respect to the light. So if it is homogeneous isotropic distribution of orientation of molecules in ensemble, it will come to this 4 over 3 pi. If one knows for sure if it is a single molecule oriented at a certain angle, then one needs to look for scalar product of electric field and vector and transition dipole. So this expression for transition dipole, which is implemented in the code oscillator strength that we were using, is tightly related to the concept of so-called Einstein coefficients. So would you please raise your voice and tell if you ever heard about Einstein coefficients? Okay. Now let's do opposite. If you never heard about Einstein coefficients, please let me know by unmuting your microphone and telling this. Like, should I cover it a little bit more?
I have never heard of it.
Oh, okay, okay. Thank you, Rebecca.
I think just the part that's relevant to what we're covering in class would be very critical.
Okay, yeah, thank you for confirming. So here is the Wikipedia page, and some people do not believe that Wikipedia is a good source of knowledge, but for introductory concepts it's not bad. So the Einstein coefficients were introduced, big surprise, by Einstein, and they were introduced before quantitative quantum theory was introduced. So it was before Schrödinger equation, but the ideas behind this Einstein coefficients are as follows. So I'm just showing you.
I think this is related to laser, am I right?
Yes, Raju, yes, correct. So I will remove this Wikipedia page and just show my slides, but you've got an idea that it doesn't look too complicated. It's like a diagram and a simple differential equation. So the idea of Einstein coefficients is that there are 3 types of optical activity of a molecule. And for simplicity, a molecule is represented just by 2 levels, E1 and E2, with energy 1 and energy 2. So if the molecule is being irradiated by light with a resonant condition, so frequency of light is approximately equal to E2 minus E1. Then there can be 2 processes. So stimulated absorption and stimulated emission. And those are called B12 and B21. So stimulated, it takes into account the fact that it is stimulated by light. Without external perturbation, without light, it is highly improbable that system will will be promoted into excited state, right? But if you do have external light source in the resonance condition, then it will be promoted up. But since if light is continuous, if it is CW excitation, if the electric field is depends on time at the place where molecule is, and it oscillates like cosine. So it is not a pulsed excitation, but it is infinite in time. Then when all probability, all population from state 1 will be converted by 100% to excited state, what will happen next? Raju? What will happen? What will happen after the light will excite model to the excited state?
It will come to the ground state, I think.
Exactly, perfect, yes. So, and it will come into ground state very quickly, and this transition back from excited state to ground will be promoted by this light irradiation. So if the molecule is exposed to the light, then it will be cycling, circulating up and down, and those are called Einstein stimulated absorption and stimulated emission. Those are quick and proportional to intensity of light. But in addition, there is a process, like if the system is excited into excited state, and then we suddenly switch off the light irradiation. The system will stay in the excited state, but not forever. After some time, it will recombine back into the ground state, right? So we know from our scientific intuition and experience that there are no systems that stay in the excited state if it is in equilibrium. So at some time, by some reason, it will come down to the ground. Yes, spontaneously. And Einstein introduced the logical separation of these two processes, like stimulated emission and spontaneous emission. Typically, this spontaneous emission is several orders of magnitude smaller than stimulated. So A to 1 is much smaller than B to 1. So if we let system to stay alone without external perturbation, it will stay in the excited state long enough. Also, this Einstein spontaneous emission coefficient, A coefficient, is related to the lifetime of excited state. So you may have heard that lifetime is measured on experiment by like lifetime photoluminescent spectroscopy, and NDSU does have several instruments that do it at several experimental labs. It's not super expensive. It's a standard thing, and if you synthesize a material, you can find a collaborator who will measure this lifetime for you. So the the stimulated emission and spontaneous emission are differ from each other by a factor. And you do see that if you take stimulated emission, the spontaneous emission has speed of light in third power in denominator, so it will be definitely somewhat slower. And if you take inverse of the spontaneous emission rate, inverse, so the rate is measured in inverse seconds or inverse picoseconds or inverse time unit. If you 1 divide by the rate, it will be time. So inverse of the spontaneous emission will be literally lifetime. And since both stimulated and spontaneous emission coefficients are proportional to transition dipole squared and proportional to oscillator strength. But lifetime is inversely proportional to oscillator strength. So the state with large oscillator strength will live longer. Okay. And here is just a little reminder of the equations that we all were practicing for computing the spectrum. So oscillator strength times resonance condition, which establishes resonance between light frequency and transition energy. So in the absorption spectrum, we use transitions from all occupied to all unoccupied, but not all of them have substantial oscillator strength. Therefore, not any pair of states in resonance condition contribute to absorption. When we compute oscillator strength, the delta function needs to be treated numerically. Ideal mathematical delta function is not comfortable to use in numerical simulation because it has zero width and infinite height. But if we approximate delta function as Lorentzian or Gaussian function with finite width, then it is a protocol that we can implement, and it is what we do when we practice absorption spectra. So it uses this argument of the function in the square with minus, and here is the width parameter. Okay. It will be not wrong to stop here, but I want to give a little bit more heads up and progress a little bit forward in our class material. I wrote stop me in previous class because I do not want to go too far and stop in time. So when the system in molecule or nanostructure is being exposed to electric field, the distribution of charge can start moving in with time and can change its shape. And the change of the charge density due to the external electric field is what is happening. We are looking at the response of the charge density onto external field. So better let me here define it this way. Initial density plus little change. So this rho prime will be change in the density. So if we remember what we discussed before, so that total density under light excitation is contributed from ground state density, transition density, and excited state density. So we can tell that ground state is here, rho 0, and this rho prime will be transition and excited state, which we neglect. Transition plus excited state, which we neglect. And if it is only transition density, we can tell that this rho prime, this change in the total density due to light excitation will be this vector of transition densities. So I'm going to refer to the chapter of advanced physical chemistry, which is called quantum mechanics, which is called perturbation theory, but we are not going to time-dependent perturbation theory. We are not going to cover the whole theory. We are just referring to it and using outcome of the theory. So in case the Hamiltonian of system is getting perturbed, where H naught is whatever is original unperturbed Hamiltonian, and H prime is perturbation, which in our case is external oscillating electric field. Then due to this change in the Hamiltonian, we are getting change in the main observable in wave function here in the density. And there is a standard expression how to connect this change in the Hamiltonian perturbation. So there is a way to solve this problem in approximate way. It is needed to be solved in approximate because literal solution, exact solution is complicated and not always possible. But one can formulate the solution for this increment change in this density in power series as function of this perturbation in the Hamiltonian. And so our perturbation is interaction between light and matter, which includes dipole and electric field. And here I'm just repeating the definition of what are our x and y. So I will be finishing very soon. We will not go through all details today, but before we disconnect today, I want to bring a heads up what will be the outcome of the new theory. So there is a very new paradigm of the excited states and optical properties that we were not using before. So even when we plotted absorption spectra, when we did presentations, and when I was presenting these things in class, we were thinking in terms of so-called orbital picture. So I have forgotten to invite you to lean back and relax during the meeting and give you warning when to wake up and focus. But I think what is being on the display right now is most important part of today's meeting. So I invite you to focus on this figure and concentrate. So in the past, in our old life before this second, we were thinking about optical properties as transitions between pairs of occupied and unoccupied orbitals. So we were thinking that lowest line in the spectrum is transition from HOMO to LUMO. The second can be HOMO -1 to LUMO. The third can be HOMO to LUMO +1. And the next one would be HOMO -1 to LUMO +1. This is not wrong. This is independent orbital approximation which works very cool for huge systems like 1,000 atoms. But and the energies of these transitions that are coming into the spectra are transition energy of HOMO to LUMO, transition energy from HOMO to LUMO +1, transition energy from HOMO -1 to LUMO, transition energy of HOMO -1 to LUMO +1. But if we are moving from ground state DFT to the true excited state theories, there is a different paradigm, there is a different mindset. So the ground state is referred to as a state with like energy 0. And if we excite system, we shouldn't think about orbitals. We should think about state of the whole system, about Slater determinants of the excited state, about overall wave function, overall density in the excited state, which may or may not be represented as a pair of orbitals. And then our lowest transitions will be just with index E sub 1, first excited state, E sub 2, second excited state, E sub 3, third excited state, E sub 4, fourth excited state. In case attraction of electrons and holes in HOMOs and LUMOs is negligible if the molecule or nanostructure does have large dielectric constant. In several specific cases, these two pictures are in good correspondence. And approximately, first excited state is energy, transition energy of first excited state is equal to transition to energy difference between HOMO and LUMO. Approximately, energy of second excited state is transition energy from HOMO and LUMO +1. Approximately, third excited state is energy difference HOMO -1 and LUMO. Approximately, fourth excited state is energy difference HOMO -1 and LUMO +1. But those are different paradigms. In the new approach, in this so-called excitonic picture, one is not allowed to speak about orbitals. So it is just excited state, and the structure of excited state is the second, is a different question. So I am not going to give the whole theory, but today. But there is a when we start next meeting with academic purposes, there will be we will discuss the specific equation that generates simultaneously these transition energies for excited states and generates the transition density matrices for each excited state. So I'm just bringing it for your curiosity. So transition energies and transition densities. So our academic goal for the next meeting will be this this equation. So let me Control C. Control V. So I suggest we finish here. Everyone, many thanks for your dedication to the course. Everyone is welcome to disconnect. I look forward to assist with any of the research projects, and wishing you pleasant, relaxing, and maybe a little bit productive weekend. And I look forward to seeing you next Tuesday on the link. Meeting is done. Everyone is welcome to disconnect, and I'll stay here to answer questions if any.
I have one.
Please.
What key point should I take?
Please repeat.
Key point. What mesh I should take?
Key point?
Key points, yes.
So, is it Raju?
Yes.
Okay, so when your electronic density of states shows large gap, if your model is predominantly a dielectric in the electronic sense, you do not need K points, even if it is conducts electricity through ionic mechanism. And this garnet oxides, electronically they are expected to be dielectric. So you may try to do K points for your system, but it is no way a primary task. It is very secondary thing, and I do not believe it will give big correction to your main observables.
Okay. So any K points doesn't matter.
It may give you small correction, but I do not do not waste your the limited time in the remaining part of the semester. There are much more important things. If you really want to explore, use just 2 K points in each dimension, X, Y, and Z. So in your original K points file, there are 111 numbers, which means 1 K point in each direction. Replace it to 2. It will not give you sampling, but it may slightly affect the molecular dynamics and optimization. But again, this is less than 1% correction to any observable for sure for this kind of system.
Thank you.
My pleasure. So I do see there are several class members are staying connected, which may mean that there will be more questions.
Thank you. Have a nice weekend.
Oh, you too, Mahik. Thank you.
Have a good day, Dr. Clay.
Thank you. You too.
Yeah, thank you.
Thank you.
Thank you.
Thank you, Rebecca. Thank you, Jofan. Thank you, Yancho.